Yeah, so organic chemistry of cats is really what it is. Even though it's not about cats, we all know it's about cats. Or no, he says it's not about organic chemistry, huh?
It's, yeah, he says it's not, yeah, but it is.
Yeah, but it is.
So now when I say it's something about cats, we're going to know it's about oatmeal. They told us.
Sorry. Maybe. I don't know. Maybe I'm lying. Okay, so we talked about enantiomers, and the thing that we know about enantiomers is all their physical properties are basically the same, except one of the ones that we know about now is optical rotational light. One enantiomer will turn it to the left, actually counterclockwise, and the other one will turn it clockwise. Plus means it goes clockwise, minus means counterclockwise as you look at it from the light coming at you. And we use a device called the polarimeter to figure out how far that has the light has rotated. So the other cool thing is if you have all R enantiomer, let's say all of one enantiomer, you'll get one rotation for 2-bromobutane. The enantiomer of that, right, will be exactly the opposite in the other direction. So if you make let's say I had those two, and I was trying to do a chiral synthesis. I was just trying to make one of them. And I got to be like, oh, I don't know, plus 10. What would that tell me? Just in generalities. It's going clockwise, right? Which enantiomer do you think I have more of? The S, because that's the positive one, right? One of the things I want to point out, though, this is S and this is positive, right? They don't correlate. Yeah, S is just a convention that we came up with to just designate at the carbon how the things are connected. Plus and minus are actual experimentally measured. And apparently there's ways that they calculate it now. They can actually do quantum calculations and figure out how the light turns and interacts with orbitals and all that kind of stuff. I know nothing about that, okay? I'm just going to say, that's beyond me right now. Okay, so typically a couple of things to keep track of. We use the sodium D line. That's the sodium's that yellow lamp that you see on the streets or in the old street lights, okay? And we use one particular wavelength that's called the D line. If you remember, lights will give you line spectra. You remember line spectra all the way from Chem 1A? It's one of the lines in the sodium spectrum. That's the 589 nanometers. And they also specify temperature because it turns out it's really temperature sensitive. So if you have a higher temperature or lower temperature, your rotation can actually go all the way around the other direction. Okay, so you do have to be very careful about those kinds of things. But within laboratory conditions, it's pretty good. Unless you're in a lab in Alaska or something. I don't know. No idea. But okay. So no relationship between R and S and plus or minus. Okay.
So they're actually opposite of each other in the sense where S would go to the counterclockwise, but positive vacuum goes so match the.
Yeah, I guess so. Yeah, if you list them that way, that's true. And then just something else that show you that's interesting. Here's one example. At 20 degrees Celsius, it's negative. At 100 degrees Celsius, it's positive. So it's temperature sensitive. It will rotate. Okay. Do you guys know about invert sugars? It's for baking. Like you can buy an invert sugar. An invert sugar is the one that's been treated with a little bit of acid, and it breaks the sugar is chiral, has an optical rotation to it, and an invert sugar simply means that they added enough acid to it and hydrolyzed it that rotation switched the other way. So it inverted its rotation.
Why would they do that?
It's these guys that bake, I don't know. I think it's something about the properties of the sugar for baking. I don't know. I don't know that.
It just sounds like
It probably tastes different. It probably handles differently. There's probably something about it. I have no idea. I just put sugar and stuff. So
maybe not as many people will end up in the hospital.
Dying,
Yeah,
from
like
diabetes.
Yeah.
Yeah. No chance. It's all sugar. Okay, so optical rotation, unlike the configuration, the optical rotation can only be determined experimentally. And if you have a racemic mixture, you have equal amounts of the two enantiomers. One wants to turn it to the right, one wants to turn it to the left. What do you think happens to the light? Nothing, right? It stays dead center. So a racemic mixture has no optical rotation. I don't know why they even put this question on here, but maybe I should ask you. How would you predict the rotation of sample 2-methylbutane? 2-methylbutane? Predict. First of all, there's two things wrong with the question. First, you got to draw it. Let me draw it. But I wouldn't. You shouldn't even have to draw it. 2-methylbutane looks like that. Well, does it matter if it's a wedge? Because I have a methyl group, right? And a methyl group.
Oh, yeah.
Not optically active. One, it's not optically active, so the optical rotation would be 0. This is not chiral, right? Has to be chiral to possess a rotation. And the other thing, you can't predict them. You just said right here. You can't predict it. You have to measure it experimentally. So I wanted to make that point. It's like one of those questions that you read and you go, well, there's just no good answer to that. But I guess to go through the thought process is good. Okay, so there's this thing when we do chiral synthesis and we're trying to produce one of the two enantiomers, okay? What we do is we measure what's known as the enantiomeric excess. What does that sound like?
Enantiomeric excess.
It sounds like, yeah, enantiomeric excess. How much more of it, one enantiomer you have than the other? How do you think you're going to calculate it for 70 and 30, 70% R and 30% S? Yeah, take the difference. So in this case, the EE, what is it? Yeah, it's 40%. 70 minus 40, or 30, sorry, see, I already screwed up. 30%, 40% excess. That means there's 40% more, all right, of the R than the S. Which way is the light going to be going? Remember, oh, sorry, which one's the R up there? Which one's the S again? The one on the left is the R and the one on the right is the S. He does this all the time in his slides. So which way is the light going to be rotating?
Counterclockwise.
Counterclockwise. It'll be going to the left in the minus direction because there's more of the minus than there's the plus. Okay? Okay, now, let's think about this, and then I'm going to show you the equation. I just want you to think about this. You could actually, from this, calculate how far the light is going to rotate.
Just by the amount of excess?
Just by the amount of excess. But think about it like this. 70% wants to turn it counterclockwise. 30% wants to turn it clockwise, right? So only 40% of it is actually going to make it turn because 30% balances out and keeps it at 0. So this number, the 40, could be used, the 0.4 could be used with this to calculate that it's 0.4 times that rotation to the left. Okay? Because everything before the 0.4, that excess, makes it racemic, looks racemic.
So the negative 23.1 and positive 23.1 are assuming that those are 100%?
Yeah, those are the 100% of the rotation.
So 0.4 of that.
Yeah. So if you want to calculate an enantiomeric excess, actually, from optical rotation, it turns out to be pretty easy. You just take the observed rotation divided by the pure. So in this case, let's say it was 10. You observed 10, then it would be 10 divided by the pure, right, times 100%. And you know which one you have the excess of because it's either going to go to the right clockwise or to the left counterclockwise. Okay, so we're doing an experiment here. We get 4.6 as degrees as your optical rotation. So you want to calculate the enantiomeric excess. It's fairly straightforward. It's just going to be 4.6. And you know what? I ignore the sign when I do this calculation, and I just figure it out later. All right? like I ignore like which one's in excess. I just do the calculation. Yeah. So you just ignore the signs, calculate the excess. But then you have to know which one's in excess, and you do that based on what the actual sign is. So 4.6 divided by 23.1 times 100. I think it comes out to be like 19.9. Ooh, it showed up in my slides. Sorry. So 19.9. I told you I was working out of 2 different drop boxes for a while. And I typed all the answers into one and not into the other because I didn't know I had 2 drop boxes. I'm like, where'd all my changes go? I made all these slides. Where'd they all go? And I'm thinking, stupid Windows, you know, all those things you say. And then you just realize, oh, no, I'm stupid. So, sorry. Percent? Yes, percent. Okay, so what does that mean? 19.9% enantiomeric excess. That means I have 19.9% more of one than the other. So how do you figure? I'm going to call that 20 because, right, because it's Monday morning and it's early. So this is the way I think about it. In order to get the actual percentages, if your brain doesn't work like this, okay, like I don't know, I can't do it, okay. I just take half of this number, okay, 10, and 50-50 would be enantiomeric, right? I mean, would be racemic. So it'd be 10 plus the 50 and 10 minus the 50. And those are the numbers that tell you the actual amount. So 10 plus the 50 would be 60, and 50 minus the 10 would be 40. So it's 40 to 60 enantiomeric. So it's a 60% of one, 40% of the other.
60% yes, and then 40% R?
Yeah, so which one did I get? I have a plus 4.6, right? That's more of this. This is the S. So there's more S than there is R. And this calculation, if I had actually done this, then the one on the right, there's an excess of that one. That's 60%. And that's 40%. Okay. If you want to put it in equation form, it looks something like, oh, it's not there. Good. It's on my slide, the little notes I made to myself. If you want to see what I wrote, it just looks like this. So 50%, to do it, 50% plus or minus, right, the EE divided by 2. And that gives you the values. So you take the enantiomeric excess, which you get from here, right, divide it by 2, and you add it to 50 and subtract it from 50. And that tells you what each enantiomer is. Okay, so and I'll tell you, it's hard to go fast at 7:30 in the morning. Really hard. So now we've like beaten to death one stereocenter. Now we will beat to death 2 and more stereocenters, okay? So constitutional isomers, you know what those are. This is to connect differently, different molecules, different properties, different everything, okay? Then we have stereoisomers. And stereoisomers are non-superimposable, okay? And they're either mirror images, or it turns out if you have 2 stereocenters, they don't have to be mirror images. So we'll talk about that. The ones that are mirror images always are called enantiomers. Okay, so if you have one stereocenter, the 2 compounds are known as enantiomers, but as long as they're mirror images, they're called enantiomers. So the other ones are called distereomers. If you're going to talk about this kind of stuff, right, cis and trans are non-superimposable, and they're not mirror images, so they would classify as distereomers. Okay? Just so you see that. Not that people really talk about them as being distereomers as much. So, okay, now I have a compound. This is known as a cyclohexanol. So this is the 1 carbon is trans. This is 2. So This is 2-methyl cyclohexanol. You don't have the alcohol nomenclature yet. But if it's an alcohol, we just get the ane and make it OL. Okay? Take the E off and add OL. So this is 2-methyl cyclohexanol. I'll write that out for you so you have it. Oops. Got rid of the E, made an OL. So what we want to do is write out all the enantiomers for this compound. Make a little whiteboard. Let's see, graph paper? Hey, you can't tell it's graph paper on it. Great. So, sorry. We're going to draw all the stereoisomers. I said enantiomers. All the stereoisomers of this compound. You just see little dots on there.
Yeah, they're little dots.
They're actually lines, graph paper.
Really?
Yeah, it's just a horrible projector. So I'm going to draw. I'm going to start like this. Oops, I'm not going to start like that. I'm going to start like this. I'm going to draw. Well, that's a reasonable size, like this one. Okay, and I'm going to draw both of the groups forward. So what would that be? But they'd be wedges, and they would be cis together, right? So I have an OH, and then I have a CH3. So that's one of the stereoisomers. I'm going to draw another one. All I'm going to do is I'm going to take one of the groups, I'm going to flip it to the back. It doesn't matter which one, I'm just going to flip one of them to the back. Okay, and now I'll keep the OH in the front for this one. Does it matter? No, it doesn't. As long as you do this systematically. And I'll put the CH3 in the back. What else can I do? So, oh, that's a horrible. Hang on. Okay, yeah, CH3, the OH in the back, and then the CH3 in the front. So now I kept the OH in the front here, all right, and then I moved the other one back. Now I move the OH to the back. I put the other one to the front. What's the last combination? Both of them back. Yeah. I'm going to blame the pen for my drawings. It's not true. So those are the 4 stereoisomers. Okay? Now, remember the rule. There's a little formula I gave you, 2 to the n. Every stereoisomer, right, gives you another pair of stereoisomers. Or every stereocenter, I should say, gives you another pair of stereoisomers. And so if you have 2 stereocenters, you'll end up with 4. So 2 to the n, this is 2, so that's going to be 4. So those are the most I could draw. Those are the 4 possible ones.
Does that not apply to meso?
Yeah, it doesn't apply to meso. This is the most you can make, and meso eliminates one. We'll get to meso in just a second. So, so the question is, which ones of these are actually distereomers, and which ones are enantiomers? Enantiomers are mirror images, right? So I'm going to label these A, B, C, and D. And I'm going to say enantiomers and distereomers. So, can A and B be enantiomers? No, because one's going forward on one side and one's going back, so there's no way they could ever be rotated where they'd both be on the same plane. So, A and B are distereomers. Okay. What about B and C? So you guys see it, I hear that people saying they're enantiomers. But in order for them to be enantiomers, they have to be mirror images, right? So what you're going to have to do is, in your head, try to make them mirror images, or you can name them. Okay? Now, in my book, it's much easier to flip it around in my head to see it. But if you're not sure, the best way to determine whether or not they're enantiomers is to actually designate the RS configurations at every chiral carbon. And in enantiomers, the thing that happens is all the centers are reversed. So if you have an RS, the other one will be SR. If you have an SS, the other one will be RR. Okay? Every center inverts because it's a mirror image at every center. Okay? So, but the way I do this is I look at these two, like these two here. And this is in the back and this is in the front, right? So I want to set it up as a mirror image. I would flip this over on the paper. And then this goes to the front. And this one goes to the back as you flip it over. And that'll be exactly the mirror image of this one. Okay? So these two are actually mirror images of each other. B and C are enantiomers. What other enantiomeric pairs do I have? A and D. So the distereomer thing gets really messy. I could pick out a bunch of pairs that are distereomers of each other. But what I tend to say is that A and D are distereomers of B and C. Okay, so I have enantiomeric pairs and distereometric pairs. Oh, sorry. It says B and C, and that's the doceri thing, because they told me they're going to get me a license. They haven't yet.
So instead of writing out all the different...
Yeah, don't write all the pairs, because like so many.
Yeah, so...
You could say B is a distereomer of A, and B is a distereomer of D, and C is a distereomer of A, and C is a distereomer of D, and then that's the list.
Just to kind of...
Yeah, just group the enantiomers together and say they are distereomers of. Right. So one line makes you happy.
What does the bottom line say?
Yeah, so it says A and D. It says, that's a stupid thing. Well, they told me they were going to get me the license and it would go away. Don Lopez. And they haven't done it yet. So that's why this is in all my videos still. And in order for me to put them back on without this silly thing, I have to re-upload every video. Yeah. So that says A, comma D, are distereomers of B, comma C. Here, let me do this. Let's see if I can do this. Rather, yeah, then. There, I moved it out of the way. That's what it says. You can cut and paste on the screen. It's nice. Well, let's look at, there's 3 stereocenters, right? 3 stereocenters means 2 to the 3rd, 2, 4, 8 possible stereoisomers. What are the relationships? They put green boxes around things. And a lot of times publishers just put green boxes and things around things just to make it pretty. But this is actually functional. Okay? What do you notice about these two compounds? They're enantiomers of each other. Because if I flip this one over to make it a mirror image, and thankfully they didn't make it so I had to rotate it, just flip it, right? This would be the enantiomer of this. What do you notice about the configurations at each of the centers? What's S is R and what's R is S. Yeah, it completely inverts. Same thing's true for this one, right? Take this one, when I flip it, the CL, this CL would be in the back. These two would be in the front, and they would be mirror images. If you notice, all the configurations are inverted. Okay? So in essence, a couple of things happen. You get all the possible combinations of R and S for your stereocenters once you've completed drawing all the stereoisomers. And that enantiomers, they're opposite at every single center because basically when you take the mirror image, you take the mirror image of every center and every center inverts at that point. Okay. So, how many, there's 2 to the end we talked about. Here's cholesterol. Now, I'll just tell you, I think there's only one of these found in your body, but I'm not sure of that. Based on 2 to the n, how many stereoisomers could you make of cholesterol? What's the n?
I'm going to discuss one.
8? 1, 2, 3, 4, 5, 6, 7, 8. So we can hide. There's a lot of them, right? Oh, come on. You can do powers of 2. No? Maybe not. There's 1, 2, 3, 4, 5, 6, 7, 8. So I just have to do